So we talked about this last time when you guys might have been gone. These last 3 days here of class, we're going to do the Chapter 12 notes. Won't do any assessment of Chapter 12 till we get back from break. But the Chapter 12 homework is your final homework set for Sunday. So that's what we've been doing. So today we're going to look at 12.2. In 12.1 we talked about probability distributions in general, and we talked about there being two types, discrete and continuous. Today we're going to look at one particular discrete probability distribution called the binomial distribution. So a binomial distribution is the probability distribution obtained from listing the outcomes of a binomial experiment. A binomial experiment has the following properties. There are a known number of trials performed. Each trial has two outcomes, i.e. success or failure, and these outcomes do not need to be equally likely to occur. So it doesn't have to be like a coin flip, it could be anything. The probability of success is constant from trial to trial. That means that these trials are independent of one another. So if you know the number of trials and the probability of success, you should be able to figure out everything else for your distribution. Also known that since there are only two outcomes, success and failure, if I know the probability of success, then the probability of failure should just be 1 minus the probability of success, right? Because it has to be 100% something happened. Is okay with this? So lots of real world events can be modeled with a binomial distribution. So for example, if you're like a basketball player and you're a 78% free throw shooter, you can find the probability that you make 10 free throws in a row. Would be something we'd use a binomial distribution for. Or if you're talking about every time you go on a car ride, the probability of getting an accident is 0.01%. We can find the probability that you'll get into an accident given that you ride in the car 2 times a day for the rest of the year. You can do things like this. Lot of real world activities that are considered just either it happens or it doesn't can be described using a binomial distribution. So the symbol, the notation that we use to describe a binomial distribution is x is our random variable. And we have this little swiggle. That means it follows the distribution. The capital B means binomial. N is, again, the number of trials, and P is the probability of success. So that's just the notation that tells us, in a problem, you'd be okay, here's the, X represents blah, 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 here's the scenario. And then they would say something like this to tell you, okay, to calculate these probabilities, I'm going to be using a binomial distribution. So determine the probability of getting exactly 2 heads in 3 tosses of a biased coin for which the probability of heads is 2/3. So one way we could do this, the way we used to be able to have to do this, was drawing a tree diagram, right? So we have heads or tails, toss 1, 2/3, 1/3, heads or tails, toss 2, and toss 3. And we'd have to go and count out. So this one is 2 heads, that one's 2 heads, that one's 2 heads. Hi, Mr. Whalen.
Hello. Do you have a note card?
A note card.
I don't know.
Like the half sheet for the test we took like a while ago.
You were absent,
Mm-hmm.
so there's no note card,
Oh, okay.
All
right?
then.
That's only for if you were present on test day.
Got it. Thank you.
Yep. It was for like the identities one, so it's not like it's gonna help you much anyway. So you have the identity sheet with you.
Oh, yeah. Is for true.
Yeah, she was trig. All right. So exactly 2 heads. There's 3 of those, so we can we can go and follow along our path. So 2/3 times 1/3 times 2/3, or 2/3 times 2/3 times 1/3, or 1/3 times 2/3 times 2/3. Either way, we get that. And we add those all up. We got 4 out of 9. Now, what happens if we're talking about like my free throw example where it's like we're going to talk about 10 branchings? Yuckarooskies, what a confusing, like convoluted mess that tree diagram is going to look like, right? Turns out that there's a better way to do that. So let's take a look at what we learned here and try to extrapolate that into a more systematic way of doing it that doesn't require a visual. So few important things. So we note that the end result is all that matters. So the probability of getting exactly 2 heads doesn't change depending on the order you get the 2 heads, whether you got head, head, tail, or tail, head, head, or head, tail, head. The probability of any one of those 3 outcomes was identical. Everybody's okay with that? And since the order did not matter, once we find the probability of one outcome, we find the probability of one of those 3 situations, we could just figure out how many times I can get 2 heads and multiply that probability by the number of ways that that can occur. So what we're talking about here is something called a combination. So that's going to be the number of ways something can occur is the number of combinations. So the number of ways you get 2 heads in 3 tosses. But just like we had intimated here, well, a tree diagram's fine, but if I have to do like 30 coin tosses, ay caramba, I'm going to be here all day drawing a picture and like trying to sort through that thing. What a nightmare. So here it says, find the probability of getting 2 heads in 6 tosses. Yikes. Let's try to do this without building the tree diagram. So first thing I'm going to observe is that we are doing a binomial distribution, right? Because we satisfy all those stated conditions. We know that there are going to be 6 trials. We know the probability of success or the outcome is one of 2 things, either success or failure. We know the probability of success is 2/3, and that's constant from trial to trial. And we know coin flips are independent of one another. So those are the 4 criteria that we need to have a binomial distribution. So we can say, okay, well, our random variable x then is represented by the binomial distribution 6, 2/3, where 6 is the number of trials, that's 6 tosses. 2/3 is the probability of success. So we know from our previous example, no matter which way we get our 2 heads, whether it's heads, heads, and then 4 tails, or if it's tails, head, head, 3 tails, it doesn't matter the order in which I get those 2 heads. It's the same probability. So we'll just find the probability of one of these and then use that result. So if I want 2 heads, I'm going to have 2/3 for a head, 2/3 for heads, and then 4 tails, so 1/3 for each tail. So that's my probability for any 2-headed or 2-head outcome. So now that we know that all the outcomes with exactly 2 heads will have the probability above, we just need to find out how many different combinations there are to get 2 heads. So to think about this, a combination is a situation where we order the individual outcomes, or where the order of individual outcomes does not matter, meaning you do not care if you get a head, head, tail, 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 or tail, 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 head, head, head. The formula for combination is as given. So there's a couple of different notations that you might use. So in your calculator, the combination notation looks like this. Most commonly in a textbook, we write combinations like this. Kind of looks like a fraction, but notice there's no fraction bar here. Don't accidentally write one, because now all of a sudden you've written the fraction n over r, not the combination. And the formula to actually compute this is this guy. What do these exclamation points mean again? That's called a factorial. And what that means, if I have like the number 4 factorial, that means 4 times 3 times 2 times 1. You guys kind of remember that probably from pre-algebra or algebra. Okay. And once again, the n is the number of trials total, and the r is going to be the number of successful trials. So in our case, we want 6 choose 2 is what we'd be doing. And just as an aside here about factorials, 1 factorial is 1, 0 factorial, also 1. That seems strange to you, but remember what these factorials are used for counting. So if I'm looking at how many ways I can arrange 0 things, well, there's still one way, right? It's like just where there's nothing there. So that's why 0 factorial is still 1. It's because it's a counting thing, not a multiplication thing. All right. So we should also note that saying 6 choose 2 is the same thing as 6 choose 4, provided that when we say 4, we're talking about 4 tails, right? Because anytime I have 2 heads, I'm going to have 4 tails. So I could also do this by counting the number of ways I can get 4 tails. Doesn't really matter. You get the same number either way. All right, so I'm going to take my probability of getting 2 heads for some 2-head situation and multiply it by the different number of ways I can get 2 heads. So I plug the 6 and 2 into my combinations formula. Go ahead and do that. Do a little reducing. Grind that stuff through on the calculator. And I get around 8%. So far, so good. Now, we're not going to do it that way, though, because, well, it turns out there's an even more systematic way of doing that. What I just showed you is our bridge from going from a tree diagram to the way we're going to try to do this in practice. And that's taking advantage of this binomial distribution. So in the previous example, we observed that this coin flipping situation fit all the criteria for it to be a binomial distribution. So here's the beauty, is all binomial distributions, we can compute the probability of our successes the exact same way. So the formula here is just going to be n choose r times p to the r times 1 minus p to the n minus r. And that's our formula. You don't have to worry about how many different ways we can count these things. You don't have to talk about the probability of success for like a single outcome. We don't need that. All we need is n and r and know it's a probability, or know it's a binomial distribution. Okay. All right. So again, this formula is one we'll use all the time. It's something that would be provided for you on a test or also the IB exam, but it's also built into your calculator. So let's take a similar situation and just rewrite it using symbols and notation. So it says X is binomially distributed with 6 trials and the probability of success equal to 0.02 for each attempt. Rewrite the situation above using symbols. So we know that N is 6 and P is 0.2. So we can write this situation as X and then squiggle B parenthesis 6 comma 0.2 parenthesis. Everybody's okay with that? So if I ask you to write the binomial distribution, that's what we're talking about doing. Pretty straightforward, right? You're just plugging in N and P into a form. Okay. So to find the probability of getting exactly 4 successes, so that's going to be 6 choose 4 times 0.2 to the 4th times 1 minus 0.2 to the 6 minus 4. So I'm just plugging it into this formula. All I'm doing is plugging in N and P. And then I can just grind that through on my calculator. So far, so good. What if we asked to find the probability of getting at least 1 success? What does at least 1 success mean? 1 or more, right? So we'd have to calculate this probability, we'd need the probability of exactly 1, exactly 2, exactly 3, exactly 4, exactly 5, and exactly 6, and add those all together. Boy, that seems like a lot of work. Is there an easier way of doing this? You could say, yes, we could do this instead as 1 minus the probability of not at least 1 success. What is the negation of at least 1? Would be less than 1. How many successes can we have less than 1? Just 0, right? So instead of calculating 5 probabilities and adding them together, I could just do 1 minus the probability of 0 successes. And boy, that seems like a much better deal to me. Although it's not wrong, to do it the long way. My life is complicated enough. I'll take the easy way out if I can do it. You know what I'm saying? All right, so again, that at least or at most is off. Yeah, sure. Is the cue to use that complement rule, the 1 minus the negation. So we noted that or at least 1 success, the negation of that would be no successes. So I can calculate the probability that X is 0 or 0 successes. So I plug that in, and I get that. So if I do 1 minus that, there I go. That feel okay? The probability of getting 3 or fewer successes. So here we're somewhere in the middle, right? So let's count. If I do this 3 or fewer, I need to count the probability for 3, for 2, for 1, or for 0. If I do it as a complement, I need the probability of 4, 5, and 6. Which one had less things to find? The complement side, which is probably the route that I would go. So again, if I do this directly, I would need to find these. If I do this as a complement, I think I forgot to write plus p of x equals 6 there. That's a oopsie. Let's pop that open and change that real quick. Yeah. I forget what button you have to press to make the PowerPoint want to pick up where it left off, but I can never figure it out. Blah, 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 blah. Sorry, guys. You ever struggle with PowerPoint? I kind of hate it. Oh, that was the slide I wanted. I prefer doing like it all myself, but anyway, so here we're at. So apparently in the PowerPoint I said we're going to just stick with doing this directly. I would have still done it with the complement because instead of 4 probabilities calculated, I only have to calculate 3. But apparently I wasn't thinking when I wrote this thing. Or maybe this was one of Mr. Chun's. I can't remember who wrote which ones. So we need to calculate these 4 probabilities. So again, I'm just using that binomial formula. Blah, 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 blah. That's what I'm typing into my calculator. That's what I'm getting. Do another example. The probability I get a bus to work on any morning is 0.4. What's the probability that in a working week of 5 days I get a bus exactly twice? So again, rewrite the symbol using symbols. So this is clearly a binomial distribution because there's a success or failure. Either I ride the bus or I don't. So if x is the number of days I get the bus, the probability of a success is 0.4. There's 5 days in the week, so that's n. So my probability, or x is binomial distributed 5, 0.4. And we're interested then where the probability of x equal to 2. So just plug them into my binomial distribution formula, grind that through on the calculator, and there you go. Let's talk about using our calculator now finally to do this, right? Like you've said, I've shown you setting it up by hand and kind of saying, and then we'll just do this on our calculator. Let's actually show it. Okay, so if you have your graphing calculator with you, I recommend you taking it out to follow along. So you'll begin by pressing the second button and the vars. Notice on the picture that's where I've circled. That's going to open up the distributions menu on your calculator. So second and then vars. From the distributions menu, you want to pick binomial PDF. In general, the difference between the PDF and the CDF the probability distribution function, the PDF, and the probability cumulative function is a CDF. If I want one value, like the probability that x is equal to 2, I want the PDF. If I want a bunch of values, like the probability x is less than or equal to 2, then I want the CDF. So since we want only x equals 2, we want the PDF. The number of trials is 5. The probability of success is 0.4. The number of successes is 2. So I type those into the menu and then press enter. And bingo bongo, there's our answer. Notice that I didn't even have to use the formula with the combinations and all that mumbo jumbo. The calculator just did it for me. Ooh, no wonder you're willing to give us the formula, Mr. Kulik, because I don't really need it. All right. What if I want at most 2? So x is less than or equal to 2. That means this, right? Then we have to add up these 3 probabilities. Or I can just use the CDF version. So if I go and I do second and then vars, I pick binomial CDF and enter it as 5, 0, 4, and 2. Bloop. Spits out exactly the same thing as I would have gotten if I did the PDF for 0 plus the PDF for 1 plus the PDF for 2. It just cut through the hassle of having to do that. So if I have my calculators, the complement thing that we were talking about earlier, that big of a deal? No way, man. The thing you have to worry about, though, is that the CDF is always only works for a less than or equal to. If it was a greater than or equal to, you can't do a CDF on it without doing some manipulation first. All right. What is the probability that... I'm sorry, when administered a drug, it is known that 80% of people using it were cured. The testing program administered the drug to 2 groups of 10 patients. What is the probability that all 10 patients were cured from both groups? So, first thing I want to recognize is that this is a binomial probability because either you're cured or you're not. That's success or failure. And what happens to one person is independent of the other, right? So we have our conditions. And let's say X is our group of patients. So the probability of getting 10 people cured is this. That's the binomial PDF that I used to do that, or I could have grinded through all that work. But remember, there are 2 groups here, right? 2 groups of 10. So I actually want the probability of x equals 10 times the probability of x equals 10. Both things need to happen. So I just took my answer here and squared it. So I get just a little over 1%. Not real good odds that's happening. I ask here, what is the other method of solving this? What is the other way we could have thought about this problem? Since I know that binomial distributions are independent, instead of thinking about this as 2 groups of 10, where I need 10 cures and 10 cures. I could have also thought about it as one group of 20 where I needed 20 cures. So if I chose this instead to be N is 20 and R is 20, and then did the same thing, I would have gotten the exact same answer. So you could have thought about it that way as well. Next thing we're going to talk about are expectation and variance with regard to these binomial distributions. So if I want to calculate the expectation of a binomial variable, it's just n times p, the number of trials times the probability of success. Doesn't matter the binomial distribution. Every binomial distribution, I can compute the expectation by just doing n times p. So for example, if I toss a fair coin 4 times, well, there's 4 trials, that's n. It's fair, so the probability of success is a half. I'd expect 2 heads to come up. Everybody's okay with that? Let's look at an example. A biased dice is thrown 30 times and the number of 6s seen is 8. The die is thrown a further 12 times. Find the expected number of 6s for these 12 throws. First question. What type of probability is this? Is this experimental or theoretical? Experimental. Why is it experimental? We haven't been given the probability of rolling a 6, right? We've just been told the result for some trial. So what are we going to use for our probability of getting a 6? 8 out of 30. Because that's what we observed from the experiment at the start. Does that feel okay to everyone? Okay. So the probability of getting a 6 is 8 out of 30, or if you want to reduce that to 4 out of 15, that's fine. Next, I'm going to observe that this is a binomial distribution because it's either 6 or not. That's success or failure. I know that dice rolls are independent of one another. That's all I need. So my binomial distribution should be 12, 4/15 or 8 out of 30. Either is fine. So the expectation, the expected number of 6s for those 12 throws is going to be 12, the number of throws, times the probability of success, 4 out of 15. So I'd expect to see 3.2 6s in those next 12 throws. Does that feel okay? Oops. Yeah, okay. The last thing we want to talk about in this section is variance. So remember that variance is the square of standard deviation. But for any binomial distribution, I can compute the variance by just doing n, the number of trials, times p, the probability of success, times q, the probability of failure. And if I want the standard deviation, what would I do to the variance? Just take the square root. So let's look at an example. In a large company, 40% of the workers travel to work on public transport. A random sample of 15 workers is selected. Find the expected number of workers in the sample that travel from work on public transport. Here we're asking for expectation, right? Expected number, which should be n times p, right? Now we know this is a binomial distribution because either they take public transport or they don't, right? That's success or failure. And what one worker does should be independent of another. I think it's fair to assume that. So we have a binomial distribution. So the expectation is just n times p. So 15 trials, 40% is the probability they take the public transportation. So we'd expect 6 of the 30 workers, or sorry, 6 of the 15 workers to be, riding the subway or whatever. So far, so good. Part B asks then to find the standard deviation of this distribution. So to do that, I'm going to first calculate the variance and then take the square root of the variance. Since it's a binomial distribution, I know the variance is n times p times q. 15 trials, 40% success, so 60% failure. So the variance should be about 3.6. And if I take the square root of that, I get this guy here as my standard deviation. So in the context of this problem, our randomly selected group of 15 workers would on average have 6 workers travel by public transportation, and any such group would on average be 1.9 workers away from that value. Right? So our random sample might have as many as like 7.9 workers riding public transport, or as few as 4.1 workers riding public transport. And that would not be surprising, right? That would be within expectation. So that's it for section 2. Let's run through some of these in-class examples here. Find what I'm looking for here. Okay. So you should probably have a calculator out for this as we kind of run through it, because really all of our binomial distribution stuff we're going to be calculating with the calculator. There are 12 students in a class, and there are exactly 5 girls and 7 boys. You want to determine the probability of selecting 3 boys in a row with replacement if you were to select only 3 students at random. So why do we need to say with replacement here? That guarantees that the probability of events remains independent. If I did have replacement, all of a sudden this becomes dependent event and a binomial distribution is no longer applicable. So that's an important statement right there. So what do we need to show for this to be a binomial distribution? How many trials are we doing? Exactly 3, right? We're choosing 3 students, so it's a finite value. Is it a success or failure on every time? Yes, because the person's either going to be a boy or a girl. That's success for boy, failure for girl. Not that girls are failures. It's just in this particular problem. The probability of success is fixed. What is it going to be? Seven out of 12, right? Because there's 7 boys in the class of 12 students. And we have independence because of the replacement. So those are the 4 things that you need to have. Fixed number of trials, success or failure. You need to know the probability of success. That needs to be fixed. And then the independence. So if I write the binomial distribution, what's that going to look like? X tilde B, and then what is N? How many trials are we doing? 3. And the probability of success is 7 out of 12. Everybody's okay with that? Find the exact value of picking 2 boys in 3 trials. So when it says exact value, what is it going to be asking for here? Probably doesn't want you to use your calculator. So we'll do the formula. So that's n choose r, so 3 choose 2, times times the probability of success to the r and the probability of failure to the n minus r. So that's going to be 3 times 2 times 1 over 2 times 1 times 1. And then 49 over 144. And then 5 over 12. So that's going to be, really just 3 times 49 over 144 times 5 over 12. I'll do that. So 49 times 5 is 245. And then 4 times 144 is going to be 5, and then, 560, and then plus 76. Yeah, sure. Find the probability that x is less than 2 using your graphing calculator. So reminder, if I'm going to use my graphing calculator for an inequality, it has to be of the form less than or equal to. I don't have a less than or equal to going on here. So let's try to rewrite less than 2 boys as a less than or equal to statement. Less than 2 boys means either 0 boys or 1 boy, correct? So that should be equivalent to x less than or equal to 1, right? And then I'll just would do the binomial CDEF on this. Anybody want to take a stab at gunning through that on their calculator? I think you get about 0.376. If you want to check that to make sure you're doing it. The next problem, where he has to find the probability x is less than or equal to 2, is already set up to do a CDF on. So just type it through on my calculator. I should get 0.802. Davian, is that working out? What?
No.
Not for you? So I do second, and then CDFs. Yep. So whenever I'm using an inequality, it's going to be a CDF. If it's an equals, it's a PDF. So for example, if I wanted to do part C, and I would do a PDF. Ugh. And I wonder if I can math frac that. Yep. Okay. And if I did part D, I would do, again, this time I'll do binomial CDF. Still 3 trials, success still 5 out of 12. Oh, I'm sorry, 7 out of 12. Yikes. I guess that previous value is probably wrong. We're looking for 1 there because we have less than or equal to 1. So there's this 0.376. If I do the same thing for the next one, but just change the 1 to a 2, get that. Looks pretty good. Does that feel any better, Davian? Okay. I'm picking on you because I saw your calculator out and you punch in, so. All right. Everybody. Example 2. Get your calculator out. Punch the numbers through. See if you get the correct values. I'll write down the answers so you can kind of check as you go. Well, the first one is a PDF because it's equals. Yep. The second one is a CDF because it's less than or equal to. The third one, you'll have to be a little bit clever about how you want to conceptualize that because the way it's currently written, you can't do it as either a CDF or a PDF because it's a greater than. That help, Jack?
Yes.
Mm-hmm. Reese, I want to say when you get a second too, I need an email of your IA file. You know what I mean?
Yes.
Okay. All right, you guys able to get A? B. What am I typing in my calculator to get C? So I'm going to need to do that as a complement. So what's the complement of greater than 6? Less than or equal to 6. So that's how I'm going to do it on my calculator. Because now I have it as a less than or equal to, so I can CDF it. Or I could have done since there's only 8 trials, I could have also done it as a PDF for 7 and a PDF for 8 and added them together. Either way, I'm going to get the same value. It's up to you on how you want to think about it, but either of those 2 ways would have gotten you to the correct answer. So what are we seeing as the takeaway here? The computation, the calculator makes this really easy, right? The hard part is understanding enough what's going on so you can recognize when it can go directly into the calculator and when do I have to kind of like play with it a little bit so I can get it into the calculator. Okay, that becomes largely the skill here. All right, example 3. Let event H be Mr. Chun checks in homework. The probability that Mr. Chun will check homework in on a given day is 0.85. Assuming that each day is independent, write the following events in correct notation and then use your GDC to solve for the indicated probability. Mr. Chun checks in homework 4 days in a row. So I'm just So to do that, what am I going to type in? Four days in a row is the key here because we're not told the number of trials, right? In the problem. So if we're talking about a binomial distribution, if everything is independent, if I want 4 things happening in a row, that just means the number of trials is 4 and the number of successes is 4. Does that make sense to you guys? So if I grind that through on my calculator, it's now PDF-able. Okay, for part B, it says, for 3 consecutive days, Mr. Chun checks in homework exactly once. In a 5-day week, Mr. Chun checks in homework exactly 3 times. So 5 days, 3 successes. in a 5-day week, Mr. Chun checks in homework at least 4 days. What does at least mean? Means greater than or equal to 4. Since we have an inequality, we know we're going to be using a CDF to do this. But the way it's currently written is not a less than, so it's not really CDF-able at this moment. Was okay with that? So to flip it, we'll do a conjugate. What is the opposite of greater than or equal to 4? Less than 4, right? But less than 4 in a discrete situation is the same as less than or equal to 3, right? And that's what we're going into our calculator now. In 2 consecutive 5-day weeks, Mr. Chun checks in homework at least 4 days each week. Oh, dang it. So it's going to be that, right? Well, we already know that probability. Because we did it in part D. All right, find the expected number, i.e. the mean or the expectation, the variance and the standard deviation for the following distributions. I'll do the first one. You guys are going to do the next ones. So the expectation is n times p. The variance is n times p times q. Thank you. And then our standard deviation is just the square root of the variance, which would be about 1.39. Colin, you got a pass here, buddy.
Good morning.
You're back. All right, who's going to tell me the expectation for part B? Or at least like tell me the numbers that I need to say in order to do it. $11 times 0.58. So that's 6.38. Okay, how about for the variance? Yeah, David.
So for the first problem, where did the 0.4 come from? Is that just like
That's the probability of failure.
so would it be 11.58
Well, it'd be 0.32, but yes. Oh, no, 4.2, I'm sorry. Yes, that's correct. So what do we get? We get 268-ish there. And then the standard deviation is again, you can just tell me what to do if you don't have your calculator out. Yeah, square root 2.68. So that's 1.64. All right. Ugh. Oops. What's the expectation for Z? Yes, good. And what's the variance?
105 times 0.27 times 7.
Yes. And then the standard deviation?
Is that just plug in square root of whatever the 1 is?
Mm-hmm. Everybody's okay? I'm not going to grind through the numbers on those. Feel like you guys can handle that, right? All right, you determine that your chances of winning a game of rock, paper, scissors is 35%. You play 6 games of rock, paper, scissors with your friend. Suppose R is equal to the number of games you win. Find the probability that R is equal to 2. First thing that we should check is this binomial distribution? Is there a fixed number of trials? Yes. How many is the number of trials? 6. Is there a success or failure? Yes, right? What is the success or failure? Well, win or not lose. Remember, for rock, paper, scissors, you can tie, right? It's not just win, lose. It's win, lose, or tie. But if it's win or not win, that's success or failure, right? Are the games independent? Yes, right? The result of one game doesn't depend on the previous game. Do we know the probability of success? Is that fixed? Yes. Is this binomial? Yes. So we're going to do this as a binomial distribution. So how do we do this then? No, just like, it's a PDF, right? N is 6. Probability of success is 0.35. R is 2. That's it. That's good enough. Find the probability distribution for R. What do I want with the probability distribution? So I want the probability for R for all possible outcomes of R. That's kind of an annoying thing to do. Let me see if we can do this in a clever way in our calculator. So these are going to be all, let me just, actually, let's say that's X. Say R equals X. Let me see if we can do this the clever way on our calculator. So these are all binomial PDFs because they're all equals. So 6 trials, the p-value is 0.35. Number of trials is going to be X. I'm going to input that. And then I'm going to go and look at the table. So I can now just like copy in here the values for P of 0, P of 1, 2, 3, 4, 5, 6. That worked. I'm surprised. I was a little worried that it wouldn't, but it did what I needed it to. That's nice, right? Rather than having to do that, jump through all those menus a bunch of different times. Hope you appreciate how much time saver that is. Okay, so I won't bother to copy those into the table, but you guys get what I'm doing here, right? Find and interpret the mean for R. When I ask for mean for a probability distribution, we're talking about expectation. What is that? What is the interpretation? What meaning does the expectation equaling 2.1 have in this setting, in the context of the problem? I would expect to have won 2.1 games of rock, paper, scissors against my friend when we play 6 games, right? That's all that's saying. Does that feel okay? Find and interpret the standard deviation. So that's going to be the square root for the variance, which is the square root of 6 times 0.35 times 0.65. So that's 117. What is the interpretation there? What would I say in the context of this problem? I would expect on average to be 1.17 wins away from the mean number of wins if I were to repeatedly play 6 games of rock, paper, scissors against my friend. Right? So if I did this again, I'd expect a value, the number of wins to be the mean plus or minus 1.17. Does that feel okay? All right. So that's our in-class examples for 2.2. Next time we'll do the We'll do 2-3, I'm sorry, 12-3. You guys should be hopefully working on the chapter 12 homeworks by this point. So we should be working on the 12-1 and 12-2 homeworks. Should all be eminently doable for you at this point. So make sure you're kind of getting started on those. Again, hopefully what you're seeing here is that these 2-2 problems are pretty straightforward if you're able to read and understand what it's looking for. The actual calculation to get the number, the calculator handles almost all of it for us. You just have to know how to ask the calculator, right? So it is one of those where, like, really try to do your homework because there's not much to write. It's not like you have to show a bunch of work, but it really helps to have, like, read the problem in practice, getting it into your calculator and getting the right number to come out and checking in the back of the book makes an enormous difference, you know, come test or quiz time, that you've done a little bit of practice here and you feel good about, like, okay, I understand, I see how these are all the same now. And I know, like, what are the little things to look for, you know, so that it doesn't feel like it's the first time trying to do it come test or quiz time. Okay? All right.